Today we're going to look at something called conditional probability. And conditional probability can be very interesting and very useful all at the same time. Let me start off by kind of introducing it with a simple comparison, something I think you're already quite familiar with. For example, let's say I rolled a die. So, roll a die. Okay, and I'm going to cover up what number I've rolled, so you wouldn't be able to see it. Now, if I said to you, what's the probability that you got, say, a 6, you'd say, that's no problem. I know that's one number out of 6 outcomes, 6 possible outcomes. Okay? But now I go and I change it a little bit. I peek at my little die here and I say, I rolled an even number. Now, I still haven't told you what the number is, but now that I go ahead and give you some information, you'd say, oh, it's an even number. Well, that changes the probability. Since I know it's an even number, the probability of it being a 6, well, there's only a 2, 4, or a 6. That's 1 out of 3. So the fact that I gave you some information had an effect on the probability. Now, that's called conditional probability. I give you some kind of a condition, and then that changes the probability in some respect. So the idea is that given information, given info affects the probability of a certain event. Okay, certain outcomes that we're interested in are affected by some information that we know ahead of time. Let me sort of help you visualize this with a Venn diagram. The idea would be something like this, and I'm going to use kind of some of the information here and some of the events. I'm going to say, well, event A and event B, keeping it really general, really simple. Okay? So here's event A, and here's event B. And if I said to you, well, what's the probability of event A? You'd say, well, it's all of what's contained in this circle that we've designated circle A. So this would represent the entire probability of A. But then I come along and I say to you, but I know B has occurred. Okay, so now I know this has occurred. All right, so we know we're dealing with this circle here that I've kind of sort of bolded here. And so what part of that is going to be A? Only this part here, the intersection. Only this has an A in it. Okay, because we know we're contained within B. So the probability in this case of A occurring, and the way this is written is as follows, and I may not have enough room here, so maybe I'll just do this over top, because it's kind of an important little relationship. Okay, if we were interested in the probability of A given B has occurred, all right, so we know B has happened, so what's the probability of A now? Well, that would be only this little part that I shaded. So that's the only part that is the desired outcome of A that's left. And that's called the probability of A and B, the intersection, as it were, between A and B, compared to all of the possible outcomes, which is all of B. So this is our relationship for conditional probability. And so the Venn diagram helps us to kind of visualize it quite nicely. I'd like to do a little example now. And what we find with a lot of these conditional probability questions is that a tree diagram really helps kind of make sense of it. Work out all the different probabilities and kind of lay it out all on the table. So in this particular example, we have two urns. Urn 1 and urn 2. In urn 1, there are 2 white and 3 red marbles. So 2 white, 3 red. And in urn 2, there are 4 white and 2 red marbles. And so what we're going to do here is we're going to walk up to these 2 urns. You're going to pick an urn, reach in, and pull out a marble. Okay? And what I'd like to find out here is we'd like to find the probability that we've reached into urn 1 if we know we've got a red marble. Okay? So given that the marble we pulled out was red, what's the probability it came from urn 1? That's kind of the way to analyze this. Now, the best way, as I was saying, is to use a tree diagram. So here's what we're going to do. First thing that can happen is either we're going to reach into urn 1 or urn 2. And because we don't know anything about these urns, the probability is simply 1/2. Okay? It's 1 out of 2 urns that you're picking. Now, whichever urn you pick, we're going to reach in and pull out either a white or a red marble. Now, if it's urn 1, the probability of white is 2 out of 5 marbles. So that's 2/5. And the probability of red is 3 out of 5. Same thing kind of happening with urn 2. We have white and red marbles. And the white marbles, well, there's 4 out of total 6. And the red are 2 out of 6. So now here's the scoop. We know we've pulled a red marble. So what that does is it eliminates certain branches, like this one, urn 1 with a white marble. That's not in the running. So what we've done is we said either this has happened or this has happened. Those are the 2 branches that have red marbles. And so what we want to do is say, well, what's the probability that we're talking about urn 1, given that we've had these red marbles come out? Well, the probability associated with this branch, and once again, a little pressed for space, so I guess what I'll do is work this at the top. So I'm probably going to need the room. So what we have to do is this, and say, well, this branch, which is the probability of urn 1 and red marble, divided by all of these probabilities added up. So we just want to have probability of a red marble occurring. And the probability of a red marble is this branch plus this branch. So we work out the 2 probabilities and add them up, and that's the probability in total of a red marble occurring. So now we just got to work out these probabilities from these branches and figure the whole thing out. So urn 1 and red is 1/2 times 3/5. And the probability of red, well, it's this branch as well, so I'm going to have it repeat 1/2 times 3/5. I'm going to add to it, plus this branch here, 1/2 times 2/6. Now that's going to be our answer, and I'm just going to clean that up a little bit, simplify it, and I guess since I don't really need this anymore, get rid of that so I got the room. You could, of course, do a lot of this on your calculator, but sometimes it's just as easy to go ahead and do it the old-fashioned way. We have 3/10 on the top, and on the bottom we have 3/10 plus, and this looks like 1/6 in its simplest form. I'm going to need a common denominator, so I guess I'll go with 30, so I'll times this by 3's, times this by 5's. So I have 3/10 over, and then my common denominator is 30, and I'll have 9 plus 5 is 14. The best thing to do now is just to take the top fraction and multiply by the reciprocal of the bottom fraction. And that leaves us with a little bit of simplifying going on. 10 goes into 33 times with a probability of 9/14. So if we know that the marble that was selected is a red marble, probability that it came from urn 1 is 9/14. Okay, so the next thing we're going to do is look at conditional probabilities in a slightly different application, this time in kind of the field of medical testing. So we'll get rid of this, and in this case now, we're going to look at medical tests for diabetes. And the information provided to us is as follows. We're going to say that the test for diabetes is accurate or correct 85% of the time. So test for diabetes is 85%, I'll just say sort of reliable. Okay? And in addition to that, we're also told 2% of the population has diabetes. So, what we're now going to be doing is answering a bunch of questions based on this information, but before I do that, I'm going to construct a tree diagram. Now, probably the easiest order to do our tree diagram in is to do the either you have diabetes or you don't, and then we'll branch off and see what the tests would say. Although we could switch that around, it seems to be more sort of common sense, or make more sense at least, if we do the idea that you either have diabetes or you don't. Okay? And then we'll branch off to see whether the test comes out as positive or negative. And the same thing down here. So let's put some probabilities in there. First of all, having diabetes. Well, if 2% of the population has diabetes, then if you randomly select a person, you would have a 0.02 probability that that person has diabetes. Similarly, a 0.98 probability that that person doesn't. If that person has diabetes and is tested for diabetes, we would expect the result to be positive 85% of the time. So 0.85 is the probability that you'll get a positive result, in other words, a true result. And negative, which means that the test kind of blundered, 0.15. Now, if a person doesn't have diabetes, we would expect that negative is the sort of expected result of the test, and of course that is 85%, and that it might falsely say the person has diabetes is 0.15 probability. So now we've got our tree diagram all set up, we can answer a few interesting questions. Something like this, for example. Probability that given the test is positive. Okay, so given that you've had this test, comes back positive, what's the probability you actually have diabetes? Okay, I mean the test we know can be wrong, but what's the actual probability that if they come back with a positive test result that you're actually a diabetic? Well, what that's going to be, and we're going to use a formula, this little formula that we're actually using, where we have the intersection of the two over the total probability of being positive on the bottom, is referred to as Bayes' formula. It's a very simplified version of Bayes' formula, and it's generally very easy to use and very friendly. The idea here is that we're going to get the probability of diabetic and positive on top, and on the bottom we're just going to have the probability of a positive result. So that's kind of the breakdown of this whole thing, and I think I'll just sort of cram that on the top here. I don't really need this extra statement there, so let's continue at the top. So what's that going to look like? Well, diabetic and positive. Well, that's this branch here followed by positive. So 0.02 times 0.85. Now that's a positive branch, and that's going to be duplicated over here. but we're going to add to it the other outcome that could be positive, which is 0.98 times 0.15. Okay, now once the thing's all set up, I went ahead and just did this on the calculator, and I got this result, 0.1037. So the probability is actually quite low. So does that make sense to us? Well, I think it does. Since most of the population isn't diabetic, if a test has come back positive, one shouldn't jump to the conclusion that it means you've got diabetes. Since the majority of the population isn't diabetic, this is a very low probability because chances are the test just kind of messed up. So kind of a good result, I guess, in a way that tests don't mean everything. So given that test has come back positive, diabetic, well, only just over 10%. Okay, I think we'll move to one last concept, and this is sort of tied in with the whole idea of conditional probability. It's an idea we've looked at before called independence and dependence of two kind of events or two experiments. We've already looked at that concept before, but just to refresh your memory, the idea is what we call independent is when the probability of some event is unaffected by the occurrence of a previous event. So whatever happens in event A, event B, the probabilities remain unchanged, no matter what happens with A. Those are independent. Now what we call dependent is depending what happens in A, the probabilities of B can be changed. And a very good example of that would be something like if we were going to take a deck of cards and draw an ace. Well, the probability of that being 4 out of 52. But if we know that somebody drew a card before this and they drew, say, an ace, well, then it's only 3 out of 51. So the probability's been changed by that information. So that's dependence. But let me get to what we have here. If two events are independent, okay, so we're going to do a little bit of an algebraic manipulation here. If they're independent, what do we know? Well, we know that the probability of A, given that B has occurred, okay, is still going to be just the probability of A. The fact B has occurred doesn't change the probability of A at all because they're independent. Now, if we use the idea of Bayes' formula and expand this thing here, well, we know that that is A and B all over the probability of B. That's just exchanging this conditional statement here with the more mathematical one. And so that equals probability of A. And we can multiply the probability of B to the other side. So we have this. The probability of A and B. Now what this means is A followed by B, those two things happening, is the probability of A times the probability of B. Now if this is the case, if this rings true, this only works if they're independent. Okay? And what this gives us is a bit of a tool to establish whether things are independent or dependent. All we got to do is think back to this. So let me do a very quick, simple little example that doesn't get too deep into analyzing the whole thing. We're just going to do a little bit of a test. So in this example, suppose we're told the probability of passing a math course is 0.75. And then we're told probability of passing chemistry is 0.85. And the probability of passing math and chem, that probability comes through as 0.7. Question is, are these, the passing of math and the passing of chem, are those independent or dependent events? So that's the big question now. Well, the simple thing is to say, well, wait a minute. We've got probability of A and B. Probability of passing math and chem is 0.7. So I'm just going to follow this and put 0.7. Big question is supposed to equal, if they're independent, probability of A, which is passing math, so 0.75, times probability of passing chem, which is 0.85. Well, here's the scoop. I don't need a calculator to see that 0.75 times 0.85 does not make 0.7. So if this doesn't work, then things are not independent. I.e., these things are dependent. So how do we interpret that if we say that these things are dependent? Well, it works kind of like this. And if you think about it, it kind of does make sense. If I said to you, okay, well, the probability that somebody has passed, say math, probability they've passed math, that's 0.75. Okay. But then I give you some information. I say, well, what would the probability be of that student passing math if you knew they already passed chem? Well, that tells you a little bit of information about that student. If they've passed a course like chemistry, chances are they're probably a pretty good student, so it's very likely that they would also pass math. So it kind of makes sense if you think about it, that extra bit of information, somebody telling you that a student, well, you know, what's the probability that a student's going to pass math? Well, let's go to an extreme case. Somebody said to you, oh, and by the way, we know that that student passed chemistry, physics, biology with honors. The probability that they passed math, I think that just went up, just based on that little extra knowledge. So that's kind of the idea behind this. That's why they're dependent, because knowing that little bit of information affects the probability of one event, like passing math. In any case, that's kind of our look at conditional probabilities, and one little spin-off thing here, which is that we can test for independence. And I guess that's where we're going to stop for today. Catch you later.